Hey everybody, welcome to our lesson video for 8.7. We're going to be looking at modeling exponential and power functions today. We've finished several chapters doing modeling, right? But when I say modeling, I mean things like regression, looking at data in different ways, and then applying it to different types of functions. So we've done this with quadratic functions earlier this year. We've done it with all sorts of different types of functions because a lot of what we're doing is trying to fit data to a model in order to be able to then use that model to predict future results. And today we'll look at specifically exponential and power functions. So if you haven't already, take a moment to set up your note sheet with 8-point section, the date, and the I can statement, and then resume the video. So to start with, just as a quick reminder, exponential functions are functions in the form y equals a times b to the x, whereas a power function is simply any function with a variable to an exponent, or in other words, a variable to a power. So these are typically in the form y equals a times x to the b. So like an example of a power function would be a quadratic function, y equals x squared, or a cubic function, y equals x cubed, or 3x cubed, or whatever. Those are all examples of power functions. So our first goal here is going to be to write an exponential function through 2 points, and also to write a power function through 2 points. So you can see some of the similarities and some of the differences. So we'll start with the exponential function first. And remember, the goal here, so we're trying to come up with a function of the form y equals ab to the x, where we want to determine what a and b need to be for that exponential function, that exponential curve, to go through these 2 points. So to do that, we've got 2 unknown variables, 2 points. That should be a hint to you, hey, we need a system of equations here that we can solve. So I'm going to create an equation for each point. So we've got 18 equals a times b squared. That would be one equation. And then our other equation would be 108 equals a times b cubed. And now we can solve the first equation for a and then use substitution into b to start out by trying to find b. So if I wanted to solve this first equation for a, I'd have a equals 18 over b squared. So I'm going to take that and substitute it in here to the second equation. And that gives us 108 equals 18 over b squared times b cubed. In other words, that's the same thing as 108 equals 18b, because b cubed over b squared is just b. So if we divide both sides by 18, that results in b equals 6. And we already know from above that a equals 18 over b squared. So if I plug in 6 for b squared, we would have 18 over 36, which equals 1/2. So then our final equation here would be y equals 1/2 multiplied by 6 to the x. That's the exponential equation that would result in a curve that goes through those 2 points. So now, instead of writing an exponential equation through 2 points, we can also write a power function through 2 points. And just as a reminder, so for our power function, we're looking at y equals a times x to the b. And again, we need to set up a system of equations so that we can figure out the values of a and b that will result in a curve that goes through those 2 points. So our first equation here would be 8 equals a times 6 to the b. And our second equation would be 36 equals a times 12 to the b. And again, we're just going to use substitution to solve this. So I would solve for a for the first one and have a equals 8 over 6 to the b. And I'm going to take that and substitute it into the second equation. which would result in 36 equals 8 over 6 to the b times 12 to the b. And the important thing to note here is 6 to the b and 12 to the b share an exponent, so we can combine them into one term. So this would be the same thing as 36 equals 8 times 12 over 6 to the b. In other words, 36 equals 8 times 2 to the b. So now we can just solve this. If we divide both sides by 8, we end up with 9 halves equals 2 to the b. And we can solve this using the log rules we just learned. So we have log 9 halves equals log 2 to the b, which is the same thing as b. We can move the b to the front and divide by log 2. So b equals log 9 halves over log 2. Now, in this case, we are going to want to actually turn this into a decimal in order to figure out our power function. We want our power function, we want a to be a single number, not an expression. So I put this into my calculator, and you'd end up with about 2.17. So now we can figure out what a is, and in order to finalize our value for this, or our answers to this problem. So a equals 8 over 6 to the 2.17. If you put that into your calculator, you would end up with 0.164. So then our final power function here would be y equals 0.164 times x to the 2.17. And that's the power function that would result in a curve that goes through those 2 points. So that's one of the things that we're going to be doing in terms of our modeling. But we're also going to be looking at some data sets as well. So I want you to imagine, as an example, imagine an entrepreneur builds a new website and keeps track of his monthly users each month. And the table below is the result of that. So our goal is to find an exponential model for this data using exponential regression. And then we want to use that model to predict the number of users in the 12th month. So it's been a little while since we did this, so I just wanted to make sure I reminded us. The other thing is we want to make sure that we check to make sure our model is any good. And we can look at r squared to tell us that, because if you remember, if r squared is closer to 1, then that tells us that we have a better fit. So the closer we can get to 1 with our r squared number, the better fit we're going to have for our data. So let's take a look at this. I'll pull our calculator up here. And if we look at, so we're going to plug in our data, so stat, edit, and then we're just putting in our 10 months first. And then in L2, we'll put in our number of users. So and then once you've got all the data in, we can go back to our stat window, go over to calc, and remember that we have a whole bunch of different types of regressions. In this case, we're looking for an exponential model. So we would probably want to do an exponential regression. So I can choose expreg. Now your calculator, if it's newer, will have a pop-up window instead, but similar concept. I can hit enter, and if I look at this, first thing I might notice here is that our exponential regression is extremely good because our r squared value is almost exactly 1. So that's a really good sign. And this tells me that my model here would be y equals 12.1 times 1.798 raised to the x. So I can add that in here. So y equals 12.1 times 1.798 raised to the x. And then if I want to predict the number of users in the 12th month using this model that fits our data extremely well, which makes me optimistic about our prediction, I would just plug in 12 for x. And then if I put that into my calculator, I'm going to end up with 13,812 users. And I can have a lot of confidence in this prediction because at least so far over the first 10 months, our model has been very closely matching an exponential, or our data has been very closely matching an exponential model. So that's a really good sign that we're doing this in the right way and using the right type of model. Because instead of using an exponential model, we could also use some sort of power model like a cubic or a quartic or a quadratic as well. So the last example I want to look at today is solving particular types of equations by rewriting a function to solve for y as a function of x that's either a power function or an exponential function. So in other words, our goal is to rewrite this equation to become either a power function or an exponential function. And essentially that means I need to figure out a way to get y alone. And I wanted to show this because there's kind of a little bit of a methodology here that you can use to come up with this. So if we look at this problem, we've got log y equals 0.2 log x plus 0.8. And there's really no way that we're necessarily going to be able to get our logs isolated on both sides because we've got that plus 0.8. We can get a little closer. We could turn this into log y equals log x to the 0.2 plus 0.8. But at this point, the only way to get rid of the log on both sides is we're going to need to exponentiate. So we can raise both sides to the 10th because we have log base 10 here. And the result of that would be that we would have y equals 10 log x to the 0.2 plus 0.8. And the nice thing here is now we can use our exponent rules to split this apart. Because when we add with exponent rules, that's the same thing as multiplying two terms that share the same base. So we could rewrite this as y equals 10 log x to the 0.2 times 10 to the 0.8. And if we do that, the 10 and the log will drop out. And we can put this into our calculator. So 10 to the 0.8 is about 6.31. And then we would have x to the 0.2. And if you notice, right here, we've got our power function. So the original equation has been solved for y, and now it's in the form of a power function instead. So I wanted to show you this because you can use exponentiation rules as well as exponent rules themselves to solve equations where you've got addition that causes you not to be able to isolate the log on one or both sides. We can still convert it into either a power function or an exponential function, depending on if there's a log on both sides, you're going to result in a power function. If there's a log on just one side, you'll use the exact same methodology, but you'll end up with an exponential function instead. So that brings us to the end of our 8.7 video. Give the homework a try and let me know if you have any questions.